Professor Clements with you as we consider more about the atom and moving on from the classical model of the atom, the Bohr model, onto the quantum mechanical model of the atom. And we'll see still some contact with the Bohr model here, that Bohr made this assumption that the electrons are in stable orbits. They are accelerated, but he said classical physics does not apply. They don't continuously radiate energy. They have more or less stable orbits. They can make transitions, but they don't continuously radiate radiation. We get the spectral lines with the photon energy being equal to the change in energy of the electron in the orbit. As further studies were done on the spectra, even in the 1800s, it was noticed that there were some changes to the basic spectral line structure when there's a magnetic field present at the atom. So that's not explained by the Bohr model. And then we have the periodic table. Is there some way that we can explain why there is this organization in the chemical behavior of elements? And of course the answer is yes. So first is stable orbits for electrons. We've talked about the de Broglie waves. For objects that are moving, the wavelength is equal to Planck's constant divided by the momentum of the object. So objects in the atom are moving. The electron can be thought of as moving, and it acts as a wave. It turns out that in the Bohr model of the atom, these stable orbits have a circumference that is an integer multiple of the wavelength of the electron. The circumference is equal to some integer n multiplied by the wavelength of the electron. So we can see this illustrated here in first semester topics of resonance, whether it's waves on a string or sound in an air tube. We have nodes and antinodes, and we get this constructive interference effect if we have the proper wavelength based on the tension and length of the string. So guitar string, violin string, or in the case of wind instruments that have an air column with a resonant, we get a certain note. So in the Bohr model, 2 pi r, that's circumference, n times wavelength, and we would have then constructive interference with this wave and itself as the electron wave, in a sense, moves around the nucleus. That's still not quite correct to talk about something located on an orbit here and moving around. If the wavelength does not, if some integer times the wavelength does not match a different 2 pi r, different circumference, then we're going to have destructive interference take place, and we will not have a stable orbit for the electron. So the Bohr orbits, we have the circumference equal to an integer times a wavelength. We get constructive interference, not destructive interference. We get a stable orbit. Here's an example for the n equals 3. There are 3 wavelengths here. So peak to peak is 1, peak to peak is 2, peak to peak is a third wavelength, and you can count for the 4. So n times lambda equals circumference. The de Broglie wavelength is connected to momentum, and momentum is quantized in the atom. We talked about momentum, mv, in the first semester. Angular momentum is mv times r in the first semester as we did that. And angular momentum is quantized inside the atom. Angular momentum is quantized. It has a value of n times Planck's constant divided by 2 pi. And again, the n's are integers. They're quantized. The electron cannot possess arbitrary amounts of angular momentum. The amount of angular momentum it possesses is in clumps. It's discrete, unique values calculated here with the n. Further studies of the light from atoms. So just the normal atom without a magnetic field present, we'd see the single spectral lines. But as we change the amount of magnetic field at the place where the atom is located, and that atom emits light, there is a change in the wavelengths of light coming out. First, notice that there are multiple wavelengths of light centered on the wavelength up here. And as we change the magnetic field, those wavelengths change. What is true about wavelength and energy? Well, they're connected. They're connected. And what we're seeing evidence of here, the Zeeman effect. The Zeeman effect is giving it evidence that the magnetic field, this external magnetic field, is somehow interacting with the electron in the atom to change the value of the energy of the electron, both in its initial state and its final state as it makes a transition. Now, the Zeeman effect indicated that there was something different happening with the energies, and notice that these energies are discrete, they're quantized. We don't have a blur of spectral lines across here and light in a whole, filling in the whole wavelength region. We have discrete spectral lines. That's an indication of another form of quantization that we'll discover here. It relates to the interaction of the magnetic field that's external with the magnetic field created by the movement of the electron. Again, it's unfortunate that we can't do any better than these drawings that show an orbit. The electron does not move on an orbit. However, it does possess angular momentum, and it does create a magnetic field due to its quote-unquote motion around the nucleus. So there's an interaction of those magnetic fields. And the magnetic interaction is quantized. There's a certain component of the angular momentum. The electron has an angular momentum that can be straight to the side here of some z-axis created by the external magnetic field direction, or it can be shifted as shown in the diagram here, or shifted in another direction to the diagram. And pretty soon we'll get to the magnetic quantum number, m sub L. It can be 0, -1, or +1 for this particular example. And we'll see this is not the only possible set of m sub L numbers. The important part in this diagram is that we have a quantization of the direction of the angular momentum, and that is causing a shift in the energy of the electron. So if the electron is in this state, it has a different energy if the electron is in the m sub L equals 0 state. And that has a consequence that's observable. The light emitted from the atom depends on the change of the electron energy. So if we start here, or if we start here and we go to some final state, there's going to be a different wavelength emitted. And the magnetic field creates a different amount of interaction, the external magnetic field, and consequently we get the different wavelengths. So this is illustrated with an energy level diagram. Don't worry about the labels, but just the energy level. Without a magnetic field, we have a single energy. With a magnetic field present, we get multiple energy levels. And don't worry about the count of how many energy levels are here. We'll cover that in a different way when we talk about the magnetic quantum number. But the important part is, with the magnetic field, this energy level splits into multiple energy levels. They should be a little bit closer spaced than what this diagram shows, but the broad effect is there. So when we have a transition without the magnetic field, there's only one possible wavelength. When there is a magnetic field, we get multiple possibilities, and we see multiple wavelengths of light in the spectral analysis. There's another effect. If you look in very closely at the at the light coming out, we'll see that even if there's no magnetic field present, the lines are actually two lines very close together. This tells us that there's another interaction, another quantization, and this one happens to be identified with quote-unquote spin of the electron in the atom. And the values here are not integers, +0.5 or -0.5. The equations of quantum mechanics produce these solutions. And quote-unquote spin, the electron, as far as we know, is a point particle. It has no size. And it has something like spin that give it a little magnetic field as if charge was spinning, but don't think of it as a basketball spinning. But it does produce this effect. We get this fine structure in the light that comes out of an atom, even with no magnetic field. So this is not Zeeman effect. Zeeman effect, there's an external magnetic field. So the quantum numbers. We're done discussing the concepts. Here's what the quantum mechanic equations inform us about. There will be solutions to the equation where we can work out the energy of the electron and the probabilities of where the electron is located only if there are 4 numbers that are selected for the electron. The first is the principal quantum number. This is the n that played a big role in the Bohr model of the atom, and it is the most important quantum number in determining the energy of the electron, and that's really the reason why the Bohr model was partially successful. These other quantum numbers have a smaller effect on the energy of the electron. So n is one quantum number. L, and our font here doesn't show the L very well, but this is an L, not a 1. The angular momentum quantum number L is a set of integers that's a list. 0, 1, 2, so it starts at 0. The last number in the list is n minus 1. So if the electron happens to have an n of 4, the possible L values would be 0, 1, 2, 3. If the n value is a 1, the possible L values would be 0. 1 minus 1 is 0. The list stops at 0 when n is equal to 1. Then the magnetic quantum number, and this was dealt with the orientation of the angular momentum, the quantization of that orientation. And the m sub L numbers start at minus L. Again, this is not minus 1, it's minus L. And then minus L plus 1, minus L plus 2 possibly, coming up to 0. These are all integers here. And then going positive, 1, 2, L minus 1, and finally L. So if the L happened to be a 2, the m sub L values could be minus 2, minus 1, 0, plus 1, plus 2. That's if L is 2. If L is 3, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Then the spin quote-unquote quantum number for the electron, m sub s, S standing for spin, plus a half or minus a half. These are the 4 quantum numbers that control the energy of the electron and the probability of the electron being in a certain location. As quantum mechanics is used to calculate these probabilities, there is this kind of electron cloud that we can think of. So here is the case of n of 1, L of 0, m sub L being 0. And it does turn out that the maximum probability, the most probable location, is equal to the Bohr radius. That's another reason that the Bohr model was partially successful. The better model, the quantum mechanics model, calculates probabilities of where the electron might be located, and the most probable location for n equals 1 is this Bohr radius. Here's some three-dimensional views, some artist views of the electron cloud for different n values, L values, m sub L values. We won't focus on those, but you should have them sort of in your mind. We do have these probability clouds where the shading is darker. That would really represent higher probability. And some more clouds to show you. L equals 0 is an S state. L equal 1 is a P state. And then these m sub L values, minus 1, 0, and plus 1. L equals 2 is a D state in our notation. So L of 2, m sub L could be minus 2, minus 1, 0, plus 1, plus 2. And then, so L equals 0, L equals 1, L equals 2, L equals 3 would be an F state. And we get more complicated patterns, probability patterns, as the L number increases. So, Wolfgang Pauli. Again, different scientists contributed greatly to the study of quantum mechanics, and you can see some of his other contributions as well. But Pauli came up with a principle regarding what numbers the electron is allowed to have for n, L, m sub L, and m sub s, these 4 quantum numbers. His exclusion principle states, no 2 electrons in one atom can have the same 4 quantum numbers. No 2 electrons in one atom can have the same 4 quantum numbers. The quantum numbers are n, L, m sub L, and m sub s. We have to have a unique set for electrons, each electron in one atom. So in one atom, this is allowed. 2 for n, 1 for L, minus 1 for m sub L, and plus a half for the spin, or 2L minus 1 and minus a half. These numbers are different. It's a different set. That's allowed. In one atom, having 2 for an N, 1 for L, minus 1 for L, and plus a half for a spin, and then a second electron in one atom, N of 2, L of 1, M sub L minus 1, and the spin quantum number again plus a half. This is not allowed. These two sets are identical. Pauli Exclusion Principle says no two electrons can have the same 4 quantum numbers. So here's an illustration of this. As we would put electrons into an atom, let's say we put into the n equals 1 state plus a half spin up and minus a half spin down. That would be allowed. As we want to put a third electron in, we can't put it in the n equals 1 level. Why is that? Well, if n is 1, L is a 0, M sub L is a 0. And the only thing that changes after that is the M sub S, being plus a half or minus a half. So this third electron must go up to the 2 state, and then could be up or down. Not allowed would be taking that third electron and putting it in the n equal 1 level with the other two. As this would be for all three of these. N is 1, L is 0, M sub L is 0. I can't have plus a half, minus a half, and plus a half. These two outer ones have the same quantum numbers, not allowed. Or the two over here, both minus a half for the spin quantum number, not allowed. Electron notation, configuration notation. The number in front represents the n number. The L value gives us the letter. If L is 0, it's an S. If L is 1, it's a P. L of 2, it's a D. And then the superscript here informs us how many electrons are in this certain combination of N and L. So that's electron configuration notation. So do you think this chart is correct? Are these in one atom, are these all legal values of the set of M, N, L, and M sub L, and M sub S? And yes, they're all legal. So I'm looking across here, I'm looking to see, are there any two electrons that have the same 4 quantum numbers? So 2, 0, 0, plus minus a half, that's legal. 2, 1, 1, plus half, minus a half, that's legal. That's a different set. 2, 1, 0, plus minus half, that's legal. 2, 1, minus 1, that's legal. So and these shells are filled here. I can't put a third electron into here. There's no other quantum number set that exists. So the 2s subshell, I can put 2 electrons into there. For the case of the 2p subshell, there are 3 different M sub Ls. Each can have 2 different spins. So I have 6 electrons possible. In the N shell, I can have 8 electrons. The N equals 2 shell, I should say. So a little reminder here, again, the symbol here is an L. L equals 0 is an S state. L equal 1, a P state. L equal 2 is a D state. For the 0 state, there's 1 M sub L value, and it can have plus or minus a half spin, so we can hold 2 electrons. For the P state, there are 3 M sub Ls. They're on this table. The P is L equals 1, and we can have minus 1, 0, and plus 1 for M sub L. Each of those M sub L numbers hold 2 electrons, possibly, so we can get 6 electrons in there. If L is 2, that's a D state. There are 5 M sub L values. What are they? If L is 2, we can have minus 2, minus 1, 0, plus 1, plus 2. So 5 M sub Ls. Each of those can hold 2 electrons, plus a half and minus a half for their spins. So 10 electrons in the D state. So let's talk about electron shells just a little bit. Hydrogen, helium, carbon, neon. Hydrogen, 1 electron. We put 1 electron in the N state. There's 1 proton, so 1 electron. Helium, 2 protons, so 2 electrons. Both of those can fit in the N equal 1 state, the 1s state. For carbon, we get 2 in the N equal 1 level, and then there's no more room. We have to go outward here into the 2s state, and then this is only showing the 2 orbit, so these, pick any 2 of these you want, would be in the 2p state. And for neon, 10 protons, so there are 10 electrons. We can put 2 in the N equal 1 level. We can put 8 in the N equals 2 level till we're filled up. So let's work this out again with the Electron Configuration Notation. I'm putting up a little chart here. This helps us decide what state we put the electron in when we have to add another electron to the atom. The states fill up from low energy to high energy is our working principle. And this little trick here, so first we go 1s, then we go 2s, then we go in a diagonal 2p through 3s. Then we go diagonal 3p to 4s. Then we go diagonal 3d, 4p, 5s. That would be the order we fill up. However, when we get into this range in the 5 level, there are quantum mechanic effects that cause these energies to sometimes be lower than what this chart would suggest. So only use this trick when you're near the beginning of the periodic table. Hydrogen, Z is the number of protons. There's 1 proton in hydrogen. So we have the 1s1 state. Helium, 2 electrons, 1s2. Again, the s state, we can put 2 electrons into that. Carbon, a Z of 6, there's 6 electrons. 2 will go in the 1s state, 2 will go in the 2s state, and we can put 2 in the 2p state. Neon, 10 electrons, so 2 in the 1s, 2 in the 2s. The p can hold 6. Do you remember why? P is L equal 1, and m sub L will then be -1, 0, and +1. Each m sub L state can hold 2 electrons, spin up and spin down. So 6 electrons fit there. Calcium, 20 protons in the nucleus, 20 electrons. So 10 for what we've done here, same as neon. And then after we filled up the 2p state, then we go to the 3s and put 2 electrons there. After we fill up the 3s state, we go to the 3p state. We can hold 6 electrons there. The next electron does not go to the 3d state. Turns out the energy of the 4s state is lower than the energy of the 3d state. So we put 6 electrons into the 3p, and then we put 2 electrons into the 4s. Are we done? Yes. 10 electrons here, 10 electrons out here. That's the Z of 20. So this tells us how we fill up the shells, at least low in the periodic table. It follows this pattern. Higher up in the periodic table, you have to use quantum mechanics and find the energies. So here is our periodic table, and especially at the edges. So on this left edge, we have atoms that have similar chemical behavior. Over on this right edge, we have atoms that have a similar chemical behavior. And right next to them, we have this white column with atoms with a similar chemical behavior. They have this chemical behavior because of the number of electrons in the outer shell. Everything over here has 1 electron in the last shell. 1 electron in the last shell. So the sodium here, that's just 1 beyond the neon that we did. 1s2, 2s2, 2p6, 3s1 would be the sodium configuration. 1 outer electron, it's very easy to strip off that electron. Now this is going to be a reactive type material, same as potassium and lithium and hydrogen. If we come over to the right side, helium, neon, argon, krypton, xenon, radon, noble gases. They filled up their shell, the last shell, and consequently don't attract an electron easily, and they don't give up an electron easily. These filled shells are stable. So we don't have ready chemical reactions occurring for the noble gases. Just short of them by 1, the fluorine, the chlorine, the bromine, the iodine, and you tell me, AT. These atoms are short 1 of filling their outermost shell, and they are reactive, seeking to grab an electron from some source when you put them with other elements that might have a free electron. So if you look at this, chlorine and sodium, chlorine and sodium, sodium and chlorine. Does that remind you of anything? Like salt, sodium chloride. But the chlorine wants to grab an electron, the sodium wants to give up an electron, and I'll let you study chemistry about atomic bonds. But Pauli Exclusion Principle, quantum mechanics, helps us understand why there is this periodic table, why there is a periodicity to the chemical behavior of elements. Last little minor topic, forbidden transitions. quantum mechanics can tell us the probability that an electron will move from one state to another state. And we have high probability transitions, allowed transitions, if the L number changes by +1 or -1. Those are allowed transitions. They're high probability. If the delta L is 0 or 2, there's a low probability that that transition will happen. And those are called forbidden transitions. They're not totally forbidden, they're just low probability and very difficult to observe on the Earth. But in our galaxy, there are gas clouds with very low density and few collisions occur. So an electron that is in one upper level and seeks to move down to a lower level with delta L of 0, that can happen rarely, but it happens more often than collisions between the atoms, such that those collisions would disturb the energy level of the electron before it engages in this forbidden transition of moving from, let's say, L = 1 down to another L = 1. So moving from a 3p state down to a 2p state. Both of those are L = 1. That's a low probability from quantum mechanics, but it is not totally unobserved. And astronomers were confused when they first saw these wavelengths of light because they didn't match what can be produced in a laboratory. But now we understand them. It's just that they have a low probability of occurring in these thin gas clouds. There's a lot of gas present. The collisions are rare. So we can have these transitions occur and observe the wavelengths of the light. So there's our ending tour of atomic physics. We saw that there is a wave nature of matter that leads to quantization. The electron wavelength times some integer equals the circumference value. We saw that there's this splitting of spectral lines when a magnetic field is present, the Zeeman Effect, that indicates there's quantization of the angular momentum, produce a different energy for the electron. And then the electron, quote-unquote, spin produces a different energy if it's spin up versus spin down. We have the quantum numbers, N, L, M sub L, and M sub S. There's a certain rule for generating the list of possible values. If you start with a certain N, you can generate the list of possible L's. You can write down the possible M sub L's for each L, and then plus or minus a half for each M sub L. And you can count up how many electrons could fit into a certain shell. So hope you read through the reading guide and textbook, and hope you bring some questions. Quantum mechanics gives us the full explanation of the periodic table. The Bohr model of the atom is incomplete, it is inaccurate. The quantum mechanic model with probabilities does give us the correct energies that we then observe wavelengths of light coming out of the atom. So a great success for quantum mechanics. It helps us understand the atom and how electrons are having certain energies in the atom, the probability of those energies, and the probability of finding the electron in the atom.